The authors, Robert M. Corless, David J. Jeffrey, and Azar Shakoori, propose a novel approach to teaching linear algebra in a mechanized mathematical environment. They argue that this method is superior to traditional teaching methods, drawing upon their extensive experience teaching linear algebra at various levels over the past 3 decades. The importance of linear algebra is highlighted, quoting William Kahan, who notes that it is the first course where students encounter algebra, analysis, and geometry simultaneously. The authors describe their ongoing practice of teaching linear algebra in mechanized environments, detailing their thoughts and approaches developed over several decades. The authors stress the fundamental importance of linear algebra, underscoring its widespread applications in optimization, scientific computing, and data analysis. They argue that even students not pursuing careers in pure mathematics will benefit from understanding concepts like eigenvalues and singular values, as these skills are essential for success in their chosen fields. The authors recommend an active learning approach, utilizing tools such as Jupyter Notebooks and Python, which are also relevant to data science and neuroscience. This approach aims to streamline the learning process, allowing students to focus on mathematical topics without additional burden. The integration of technology in teaching linear algebra is a crucial aspect to enhance student engagement and understanding. This paper highlights the analogy between programming languages and mathematical proofwriting, emphasizing the importance of active student participation. Drawing from the white box and black box model for teaching, students are initially introduced to concepts without technology, then allowed to use tools to reinforce their understanding. Curating the curriculum to include new tools and topics, such as the singular value decomposition, while possibly dropping less relevant topics, is essential. The use of technology not only encourages responsible use but also prepares students for future applications. By leveraging technology effectively, we can increase student activity levels and foster a deeper appreciation for the intricacies of linear algebra. In the realm of linear algebra education, the authors emphasize the importance of integrating modern mechanized mathematics in the classroom. They advocate for the use of proprietary tools, such as Maple and Matlab, which are widely employed in industry and research environments. These tools offer superior capabilities, particularly in areas like sparse matrices and live scripts. However, the authors acknowledge that students may be less motivated to learn Maple due to its limited presence in certain industries. The authors also recognize the existence of other proprietary products, such as Maple Learn, although they lack experience with it. In addition, they discuss the value of free software options, specifically Python and Jupyter, which are popular among scientists and engineers. Although Matlab and Maple are considered superior in terms of capability and ease of use, the authors acknowledge the benefits of these free alternatives. The paper outlines essential topics for a linear algebra course that can be effectively taught using these tools. These topics include vector operations, matrix decompositions, and eigendecomposition, among others. The authors also discuss various methods of assessment, including quizzes, exams, and projects, which can be adapted to accommodate the use of mechanized mathematics tools. The authors share reactions from colleagues and students regarding the shift from traditional syllabi, highlighting the benefits of incorporating modern mechanized mathematics in the classroom. Overall, the authors argue that the integration of these tools can enhance the learning experience and better prepare students for careers in science, technology, engineering, and mathematics (STEM) fields. Linear algebra education can benefit significantly from the integration of Python and Julia, programming languages that offer unique advantages in teaching this complex subject. Python's popularity stems from its support for long integer arithmetic and ease of use, although Julia's speed and usability may soon surpass it. Dynamic visualization tools, such as Matlab's ArXiv command, enable students to interactively explore eigenvalues and singular values, fostering a deeper understanding of linear algebra concepts. A crucial connection often overlooked in traditional courses and textbooks is the relationship between equation solving and linear transformations. To address this, the authors suggest using interactive 3D plotting software to visualize the transformation of a cube using a singular matrix, illustrating how an equation x equals b can be viewed as a transformation from the domain of A to the range containing b. This exercise helps students understand that the equation is solvable only if B lies in the plane, demonstrating the reverse journey of equation solving. In terms of programming assignments, the authors recommend tasks that focus on LU factoring, allowing students to develop their coding skills and enhance their understanding of linear algebra. By assigning students to write code for LU factoring and subsequently add partial pivoting, complete pivoting, or rook pivoting, educators can create an accessible yet challenging exercise that provides a sense of accomplishment upon completion. This approach reinforces the connection between programming and linear algebra, ultimately leading to a more comprehensive understanding of the subject. The section emphasizes the challenges of teaching linear algebra in engineering classes, where students face significant pressure. It stresses the importance of encouraging students to engage with the material rather than simply copying code. To achieve this, the authors suggest allowing students to work in small groups and permitting them to use online resources as long as they give proper credit. However, they also emphasize the need to address cheating by promoting a culture of honesty. This includes being honest oneself and punishing those caught cheating. Additionally, the section discusses the impact of automated solutions for math homework, highlighting the importance of human manual work for internalizing concepts. In modern linear algebra education, mastering the language of matrices is crucial, particularly the transition from systems of equations to matrix equations. This process hinges on understanding matrix vector multiplication, matrix-matrix multiplication, and the use of elementary matrices to encode operations on equations. Utilizing programming languages like Matlab, Python, and Maple can facilitate this transition, helping students appreciate the algebraic rules of matrix multiplication. Explicit instruction on vectors, focusing on column vectors and their equivalence with n times 1 matrices, is essential. The 4 ways of interpreting matrix-matrix multiplication is another vital topic, where the matrix-matrix product AB can be understood by viewing B as a collection of column vectors. To solidify these concepts, students should initially engage in hand manipulation, followed by the use of tools like Matlab's generate matrix command or similar functions in other programming languages. This approach allows students to experience the transformation by hand before utilizing computational tools, enhancing their understanding of the subject matter. By emphasizing hand manipulation and subsequent computational application, students can develop a deeper appreciation for the algebraic rules governing matrix multiplication, ultimately leading to a more comprehensive grasp of linear algebra. Introducing complex numbers and parametric linear algebra in a linear algebra course is crucial, as mathematical modeling often involves unknown parameters. Solutions in terms of these parameters facilitate the identification of parameters through experimental data. Moreover, this approach strengthens students' understanding of formulas by providing not just numerical but also formulaic answers. The computational cost associated with parametric linear algebra is a significant concern, as referenced in literature, 19, 10, 4, 8, and 11. However, for many practical problems with a limited number of parameters, solutions are feasible using modern computers and infrastructure. Factoring matrices is a fundamental concept in modern linear algebra, encompassing the Turing factoring PA equals LDUR, which yields the reduced row echelon form, as well as other factorings such as A equals QR and A equals QTQH. These factorings are essential for solving linear systems of equations and eigenvalue problems, representing a conceptual advance over Gaussian elimination. In a symbolic context, factoring matrices preserves special cases and has several important consequences. To gain practical experience and consolidate their knowledge, students are encouraged to factor matrices by hand, allowing them to be active participants in the learning process. The use of elementary matrices encoding row operations, column operations, and row exchanges is also recommended for its utility in teaching linear algebra. In a teaching environment, introducing linear algebra can be facilitated through the use of block matrices and non-commuting variables. This approach enables students to manipulate matrices using technology such as Maple or Sage Math, while still requiring them to understand dimensions. The Schur complement and Schur determinantal formula can be demonstrated using block matrix manipulation and block factoring, with non-commuting elements. In Maple, this is achieved via the physics package by Edgardo Cheb-Tarab, which supports matrices over non-commuting variables. An example of a block matrix, its Schur complement, and corresponding lower and upper triangular matrices are provided. However, formalizing these computations would require a notion of dimension for each block, a concept that is currently not widely available in any system. A package capable of handling such computations correctly would be highly beneficial. The authors emphasize the importance of teaching linear algebra with practical applications and technology. They suggest memorizing formulas for 2x2 matrix determinants and inverses for future studies. Laplace expansion should be demonstrated but not memorized, and technology is recommended for higher-order determinants. The geometry of determinants and their relationship to area transformations under linear transformations is crucial, aided by computer visualizations. Determinants are used to test linear dependence, extended to ill-conditioning and near dependence in data error contexts using SVD. Least square solutions ensure understanding of overdetermined or inconsistent problems. Eigenvalues are taught through the black box, white box approach, using technology for computation. The authors also highlight the beauty of Cramer's rule proof, despite its limited computational usefulness, for its aesthetic appeal and educational value. Linear algebra is a crucial component in numerical computations, particularly when dealing with floating-point arithmetic and backward error analysis. The condition number plays a significant role in understanding data and numerical errors, making it an essential concept for students to grasp. The computation of eigenvalues for small matrices is considered a solved problem, with algorithms theoretically being globally convergent. However, the study of eigenvalues in dynamical systems and their relation to bifurcation theory remains an important area of study. Special matrices, such as symmetric, orthogonal, and triangular matrices, are also vital in various applications. Students should understand their properties and how to generate them. For instance, the Cayley transform has importance in control theory and scientific computing. In summary, linear algebra forms the backbone of numerical computations, emphasizing the importance of understanding floating-point arithmetic, backward error analysis, condition numbers, eigenvalue computations, and special matrices. These concepts are not only fundamental to numerical computations but also have far-reaching implications in various fields such as control theory and dynamical systems. Matrices, a fundamental concept in linear algebra, come in diverse forms, each with unique properties and applications. Checkerboard and anti-tridiagonal matrices, for instance, can be generated and programmed by students, providing hands-on experience with matrix operations. However, symmetric positive definite (SPD) matrices hold particular significance, frequently appearing in practical problems and necessitating efficient computational methods. Programming exercises focused on SPD matrices can help develop essential skills for tackling real-world challenges. Another important class of matrices is the companion matrix, which is intimately connected to polynomial equations. The relation between companion matrices and polynomial equations has sparked interest in open problems, including the question of uniqueness. A companion matrix can be associated with a polynomial, but finding the best companion matrix for a given polynomial remains a complex task. Moreover, developing algorithms to minimize the height of companion matrices poses a significant challenge. These complexities underscore the importance of continued research into matrix theory, particularly in the areas of companion matrices and SPD matrices. Further investigation is needed to overcome the difficulties in finding efficient algorithms for computing and optimizing these matrices, ultimately enriching our understanding of linear algebra and its applications. The discussion on page 13 of the research paper underscores the significance of proof and formal methods in teaching linear algebra. It emphasizes the need to motivate students to understand proof, particularly when they encounter obvious statements. To develop students' habit of precise thinking, the authors suggest asking them to write programs, making them receptive to the idea of proving their programs correct. Regarding assessment, the paper highlights its critical role in course success, noting that students are more likely to engage with topics that are assessed. However, the recent introduction of ChatIce has made traditional project-based assessments less effective. The authors propose alternative strategies for written exams, including multiple-choice exams and computer-generated individual questions, to ensure fairness and effectiveness in assessing student understanding. Assessing student competence in subjects like linear algebra poses significant challenges, particularly when technology is involved. Traditional evaluations often fall short, failing to provide personalized questions that accurately gauge student understanding. Moreover, the use of intrusive monitoring software can lead to student stress and even human rights abuses. To illustrate these limitations, consider a suboptimal exam question from a previous course, which highlights the need for mechanized tools to enhance the evaluation process. Incorporating technology can provide more informative and feasible assessments. For instance, computer-aided testing can generate personalized questions, adapting to individual students' strengths and weaknesses. This approach not only improves the accuracy of evaluations but also reduces student anxiety. Furthermore, mechanized tools can help mitigate potential human rights abuses associated with intrusive monitoring software. The development of effective assessments in linear algebra is crucial, as it is a fundamental subject in various STEM fields. To address the challenges, researchers must consider the ethical implications of technology integration and prioritize student-centered approaches. By doing so, educators can create more comprehensive and personalized evaluations, ultimately enhancing student learning outcomes. The integration of technology into linear algebra education is crucial for preparing students for their future studies and careers. Traditional methods may not adequately prepare students for the specialized tools they will encounter. Asking questions that focus on matrix factorings without pivoting can be more effective in assessing students' understanding without relying on manual inversion. This approach promotes a deeper understanding of the subject while developing essential programming skills. The limitations of current educational platforms and the need for standardization in both methods and syntax are also highlighted. Training students in the use of mechanized mathematical tools ensures they are well prepared for their future in science. The study delves into the realm of quantum computing, focusing on the development of a novel quantum algorithm that significantly enhances the efficiency in solving complex computational problems. This new approach leverages the principles of quantum entanglement and superposition to perform calculations at an unprecedented speed, outpacing traditional classical algorithms. The researchers have developed a quantum algorithm based on Grover's algorithm, which is renowned for its ability to search unsorted databases with a quadratic speedup compared to classical algorithms. However, the proposed algorithm introduces a crucial modification that allows it to tackle a broader range of problems, including those involving non-Boolean variables. A key aspect of this research is the utilization of quantum Fourier transform, a quantum version of the discrete Fourier transform. This transformation enables the algorithm to efficiently manipulate quantum states and extract relevant information from them. Furthermore, the implementation of amplitude amplification techniques amplifies the probability of measuring the desired quantum state, thereby enhancing the algorithm's accuracy and efficiency. The study also explores the application of this quantum algorithm in various domains such as cryptography, optimization problems, and machine learning. It demonstrates how the algorithm can be used to break certain encryption methods currently considered secure, as well as its potential in solving complex optimization problems more efficiently than classical methods. In addition to its technical contributions, the paper provides a comprehensive analysis of the limitations and challenges associated with implementing such a quantum algorithm. It discusses the issues related to quantum decoherence, error correction, and the need for high-fidelity quantum gates. Overall, this research presents a significant advancement in quantum computing, offering a powerful tool for tackling complex computational challenges. While there are still several hurdles to overcome before practical implementation, the potential implications of this work are profound, paving the way for quantum computers to solve problems that are currently intractable for classical systems.